Welcome to another MVC screencast. Today we're going to look at a brief example of finding potential functions, in particularly in 3D. So you can put on your blue and red glasses now. They won't help, but you can. So let's find the potential function for this conservative field in 3 dimensions. Now when we get to curl, we'll have a test to see if a function is not conservative quickly. But we'll put that off till next week. For now, we're given that this is a conservative field, so we'll believe them. And we go and try and find a potential function. I'll remind you that just means we want to find a function, little f, whose gradient is this big F here. And just like in 2 dimensions, we'll start with just concentrating on one component, right? Might as well be the first one. Here, we'll say that the first component has to be the x derivative of this function, little f. That gives us this equation. So f itself, we know when we differentiate it with respect to x, this is what we should be looking at. So we find antiderivatives, again with respect to x. And just like the derivative counterpart, we treat y and z like a constant. So integrating is simple, it's just a chain rule and a trig rule here. But here's where we have to be careful now, right? Differentiating with respect to x will give you 0 for any function of y and z. Right, so that what is normally a constant of integration is in fact another function of the other variables, y and z. Right? If there's no dependence on x, the term will disappear, so we can't forget about it in our function f. And now we proceed, we're going to differentiate this expression with respect to y. Right here, so we just get xy for the first term, the 2's cancel. The next term has no y, so we get 0. When we get to the g, remember, we're differentiating with respect to y, so that's the partial derivative of g with respect to y now. And we want this thing to be equal to that second component, the j component up here. And so we just set them equal to each other, right? And to figure out what g is, well, we're going to cancel out like terms, and realize that now we've got an expression that the partial derivative of g with respect to y is 3z. Okay, so that tells us about g here. So we'll rewrite f, what we know about it, the same parts from above. But now when it gets to g, I know it's the y derivative is 3z. So taking an antiderivative, we get 3yz there. But then again, we have to be careful because we differentiate it with respect to y. Right? Any function of z won't show up here. So we need another function that shows z dependence. Right? And now we proceed again down the line. I'll differentiate this guy with respect to z to check the last component. Right? So there's my minus sine x when the z drops out to 3y. And then h prime of z. It's only one variable, so that's why we just have the simple prime there. Set that thing equal to the last component. Right, the k component, 3y minus sine x. It's not uncommon that we see these terms show up on both sides. So we can cancel them out, and I'm left with the fact that h prime of z is 0. Though, in fact, h is just any old constant will do. And we can finish this off by sticking it all together, right? Recognizing that h of z need only be a constant, and there's our potential function for this vector field. You might want to differentiate it just to check that we did it correctly.